Hello, everybody. Welcome to the final talk of the semester. This is the Center for the Future Mind, and we're really, really excited to have so many distinguished guests all semester. And before we get started, and before I announce our very distinguished speaker, a few housekeeping items. Okay, so the first thing I want to ask everybody is, you're on camera, so we can all see you now. So if you don't want to be seen, just, get rid of your camera function. And also same thing for muting yourselves, if you don't mind. And I apologize if you hear any background noise. I am on a farm. You will hear peacocks. Somebody's already holding up our speaker's book. So I see, a lot of excitement in the audience already. This is great. I'll keep it quick, okay? So the first thing I want to say, though, before we get started is, over the last several weeks, we have had people reaching out to us, coming to our talks, and we've added some really distinguished senior fellows over the last few weeks. So I just want to name these people and greet them to the center. I hope I don't miss anybody here. So first, the founder of transhumanism, Natasha Vida-Moore. We're so honored to have her as a fellow here. Then, of course, Bernard Bars, the person who really got the ball rolling with the global workspace theory of consciousness. And in fact, we are having a technical workshop on the 13th. That's just a few days away, where Bernie's going to be discussing his new paper. And, you're all welcome to attend. I will be sending something out. Lenore Blum, who is the Emeritus Distinguished Career Professor at Carnegie Mellon University. I see you're here today. We're so excited to have you. And of course, Manuel Blum as well, also of Carnegie Mellon University and a Turing Award winner. Very happy to have you here. And Edward Turner, a dear co-author of mine and a professor of astrophysics at Princeton University, who, ever since he was an undergraduate at MIT, has been really interested in machine consciousness. So welcome, everybody. So now let me, tell you a little bit about our very distinguished speaker today. So I'm so excited to, introduce Stephen Wolfram, who I met at Harvard a few years ago and who I know gives very wonderful talks. He's the creator, as many of you know, of Mathematica, Wolfram Alpha, and Wolfram Language, and the author of a really interesting book, New Kind of Science. The originator of the Wolfram Physics Project, which he might talk a little bit about that today, I suspect, and the founder and CEO of Wolfram Research. So we're very lucky to get him. I know he's very busy. So let's go ahead and get started.
Great. Thanks very much. All right. So this is a strange kind of talk, unlike any that I've given before. So disclaimer, my mother was a philosophy professor in Oxford, and when I was a kid, I always said, if there's one thing I will never do when I'm grown up, it's philosophy. So here I am talking about consciousness. All right, so I didn't ever think I was going to have anything interesting to say about consciousness, but it's turned out that this big project that we've done about physics recently has forced me into trying to understand things about consciousness, and I want to tell you a little bit about that. Let me just say something about our physics project. I'll talk about kind of the intellectual underpinnings of that, and then I'll talk about what's actually in our physics project. But the thing that I have been kind of wondering whether it was going to happen for a long time was whether these kind of computational ideas that we had would be able to apply to fundamental physics. And starting about a year and a half ago, we realized, yes, they actually do, and it's really spectacular. These sort of fundamental theories of physics, general relativity, quantum mechanics, and so on, that originated in the 20th century, we now really understand the machine code that lies underneath those theories. And I think we really have a good understanding of how physics is put together. And what's remarkable, it's sort of a week-by-week process in recent times, has been seeing how all of these approaches in mathematical physics kind of dovetail beautifully with essentially the foundational machine code that we now have for understanding physics. All right, well, let me start off giving some of the sort of intellectual background, and I'm afraid it's a bit of a tower that I've been building for the past 40 years or so that I think some pieces of which you probably need to understand to try and understand what I think I might have figured out about consciousness recently. And I might say, by the way, if for people who are interested, so my entry into this understanding of consciousness was actually the piece that I wrote a couple of weeks ago that if people are interested, I can put the link to it in the chat here. This will probably say more clearly the things that I'm trying to talk about here than I will say them verbally. So if you're interested, please do check it out. All right, let's start at the beginning. So when I was a kid, I got interested in physics, and I got interested in sort of fundamental physics and understanding kind of how things work in the universe. I did lots of particle physics and cosmology and so on. And at some point, I kind of got to wondering, there are all these things in the universe and nature that our kind of standard mathematical models that we've sort of had for the past 300 or so years don't seem to be able to capture very well. So I got interested, this is now beginning of the 1980s, in the question of, if we are going to generalize, if we're going to take this idea of making formal models of things and we're going to generalize it beyond kind of the details of mathematics, the integrals, the differential equations, things like that. What is the sort of generalization of a formal model outside of mathematics? And conveniently, in these times, we have a great metaphor for that, which is computation and programs. And so I got interested in what would happen if we sort of generalized this idea of modeling to think about programs as models for the world. And so the programs we're used to dealing with are typically programs that we would write that will be long, complicated things that work for some particular purpose. But then I got interested in, okay, if we just look at programs in the abstract, sort of the computational universe of possible programs, what's out there in the computational universe of possible programs? You can kind of think of this as, if we think of these programs as sort of formal models, what's out there in the universe of possible formal models, the kind of universe of all possible universes. So the particular kind of models that I got, that I liked best very early on were these things called cellular automata. And this is a very simple example of one. The way it works is there's just a line of cells, each black or white, and at each step, the color of each cell is updated according to the color of the cell directly above it and to its left and right. So for example, with that particular rule, what we have is something where this is telling us the program is, in any case, this is the program, the rule. We start at the top, it's just one black cell and a bunch of white cells around it. And what we see is very simple rule, very simple behavior. So we might think, okay, we've got some, it's not surprising, it's a simple rule, it's going to do very simple things. Keep going, we look at different kinds of rules. Here's another rule, same type, slightly more elaborate pattern. Keep going, we get this kind of nested structure and so on. So then the obvious question is, if we just look in this possible, we sort of turn our computational telescope at this computational universe of possible programs, you just say, what are all the possible things that can happen? Here are the results for the first 64 of those programs. And you see many of them do very trivial things. But my all-time favorite, it's kind of my all-time favorite science discovery, is Rule 30. That's the rule for it. Another one of these very simple rules. We started off from just one black cell here. And instead of getting what we might have expected, which is simple rule gives simple behavior, instead we get this much more elaborate, complicated behavior. So this is a slightly longer version of the same thing. We can see there's a certain amount of regularity over on the left, but in many respects, this picture looks completely random. If we look at the center column of cells here, it's served as a great pseudo-random generator for us for many years. So this is, to me, a very intuitionally surprising thing. I mean, we're kind of used to, from engineering, from other things, the idea that if we want to make something complicated, we have to go to lots of effort. We have to sort of have complicated plans to make that complicated thing. But what's happening here is sort of in this computational universe of possible programs, it works very differently. You just go out into this computational universe, you find tons of programs that, even though the programs are simple, the behavior they produce is very complicated. And you can go on, you can find all kinds of different things. There's just another example. You quickly start realizing that a lot of what you see in these simple programs looks a lot like the kinds of things that nature does. And it turns out I've spent many years in probably tens of thousands of papers now that study this particular point and realize that, yes, in fact, these kinds of simple programs are good models for lots of kinds of systems in nature, whether they're plants or chemical catalysts or road traffic flow or whatever else. And actually, one of the things that's been sort of in terms of history of science pretty interesting is that for about 300 years, when people wanted to make a serious model of something in the world, they would typically turn to mathematical equations to do that. In probably just the last 20 years, there's been sort of a silent transition to new models that get made of things, almost always being models that are made in terms of programs, not in terms of equations. So the question then is, so that's kind of the sort of foundational point. Now, what happens when we start thinking in terms of models made with programs? What can we say about this behavior of Rule 30, for example? So there's a very general principle that, well, let's talk about a variety of things. So one question is, when we do science, one of the things that people are often proud of is, you know, if I can make a scientific statement about something, then I can predict what the thing will do. So in a sense, what that would be saying in the case of something like Rule 30 is, okay, I started off from one black cell. I can immediately predict in 1 billion steps, it will do this or that. And we might have thought that, in a sense, when we say we're going to do that, we're saying we as the predictors are somehow computationally smarter than the system itself. It's going to go through 1 billion steps to do what it does, but we're smarter and we can jump forwards and just say the answer is going to be this. And in traditional mathematical science, that's what we've been very used to doing. We don't have to sort of trace the orbits of the Earth around 1 million times. We just plug a number into some formula and we can work out sort of the idealized position of the Earth. But what turns out to happen in things like Rule 30 is a phenomenon I call computational irreducibility. Instead of it being the case that you can sort of computationally reduce the effort to go and find the final result, in a sense, you have no choice but in effect to just go through and trace every step of how the system itself behaves. Clearly, you can work out what's going to happen 1 billion steps from now in this picture by just tracing 1 billion steps. The question is whether you can go faster than that. And there's lots to say about the formal computational complexity and so on. I can see we have some computational complexity theory folk here. Let me not go down the rat hole of talking about that in detail here. The main point is the intuitional point of, is there computational reducibility? That is, you can jump ahead and say what the answer is going to be, or is there computational irreducibility, this kind of phenomenon where to know what the answer is, you essentially just have to trace each step. Now, that to know what the answer is, you essentially have to trace each step is closely related to things like Gödel's theorem and so on. The thing that is probably the most, so one question is, how common is this phenomenon of computational irreducibility? See, I think one of the things that, here's another example. We might ask the question, what's this going to do in the end? Is it eventually going to die out, or is it going to keep going forever? And to know the answer to that question, if there's this phenomenon of computational irreducibility, we kind of just have to trace each step. And if we say, will it ever die out? We might be stuck having to trace an infinitely large number of steps to be sure what the answer is. But one thing that's sort of very surprising in the computational universe, certainly was very surprising to me, is that this phenomenon of very complicated behavior from very simple rules, this phenomenon of apparent computational irreducibility is not this obscure thing hidden away in special, Gödel sentences and so on. It's actually something quite ubiquitous in the computational universe. And that led me to this thing I call the principle of computational equivalence, which is sort of a general principle about computational systems. And what it says is, if you see a computational system that isn't obviously simple in its behavior, then it will be computationally as sophisticated as any system. So let's try and take that apart a little bit. When we see one of these systems and we see what it does, we can think of its behavior as corresponding to some kind of computation. You can think maybe there's some initial input, then the thing crunches for a while, produces some output. It's doing a computation. The question we can ask is, how sophisticated is that computation? Is that computation something that actually it was wasting its time, we could just jump ahead and see what the answer is, or is that computation something more sophisticated? So an example of a measure of the sophistication of a computation is it something that's computation universal? Is it something where, in principle, we can set up its initial conditions so that we can have this particular system emulate any other possible computational system? So that's sort of one measure computational sophistication, we can go beyond that and ask about what it does with typical initial conditions, not just with sort of specially constructed programs. But the question, the thing that is the statement of the principle of computational equivalence is, when you're not seeing a system whose behavior is in some sense obviously simple, you're seeing a system of maximal computational sophistication. So there are predictions from that, like that the system will be capable of universal computation, like that it will show computational irreducibility, and so on. And we have got a certain amount of evidence for this principle of computational equivalence at this point. This is the very simple cellular automaton that we know is computation universal. We know that the simplest Turing machine that has kind of not obviously simple behavior is also computation universal. We're sort of progressively getting more evidence for this principle that when things are not obviously simple, they're actually of maximal computational sophistication. Okay, so let's come back to this phenomenon of computational irreducibility and try to understand that in terms of the principle of computational equivalence. So if we are trying to predict what this system is going to do, we're essentially saying we can be smarter than this system. We can be computationally more sophisticated than this system, so we can jump ahead and see what it's going to do. But what the principle of computational equivalence says is that's not going to work, because all these different systems, from the simple cellular automaton to our brains, to our mathematics, to our computers, and so on, all these systems are actually equivalent in the sophistication of computations that they can do. And that's why there's this phenomenon of computational irreducibility. We can't just jump ahead and see what's going to happen. So there are all kinds of consequences to this, all kinds of consequences about sort of why simulation becomes essential and things like this. There are also sort of more philosophical consequences, like you can ask questions like, you can talk about things like origin of free will versus determinism, and you can talk about the fact this is a deterministic system, but it has the feature that nothing can tell it what it's going to do other than it doing it itself. And you can ask questions about well, there's sort of lots of consequences of this idea of principle of computational equivalence and its implication in computational irreducibility. Okay, so that's sort of first intuitional step, is understanding this notion of computational irreducibility. I mean, in a sense, computational irreducibility is showing that science limits itself from the inside. People have had the idea that, okay, once you've got the equations, you're just going to be able to solve everything. You can solve the epidemiological equations, you can work out what's going to happen. Everything is, once you have the equations, you're done. What we're seeing from computational irreducibility is that science is explaining that it is limited from the inside, so to speak. There's sort of a fundamental limitation on what is predictable in that sense. In some sense, computational irreducibility might be sort of a downer in the sense that you say, well, gosh, computational irreducibility limits what we can do. It's also kind of an encouraging thing, because if you imagine, we lead our lives, we do what we do, and we say, what's the end result going to be? Well, if everything was computationally reducible, all of that leading our lives, in a sense, will be a waste of time. We'd just be able to sort of say the answer is 42. We can do the sort of computational reduction to answer that. We don't need to go through the sort of process of leading our lives to get that answer. Okay, so in a sense, computational irreducibility is sort of a story of the limitation of science from the inside. It's also a story of why we'll talk about later, the sort of the progress of time is actually meaningful. Okay, so one question from all of this is, we've got these simple programs, we've got, they turn out to be good models of lots of everyday practical systems in the world. The question is, what about fundamental physics? Could models like this be actually useful models for fundamental physics? Could it be the case that underneath everything we know about the universe, there's ultimately just some simple rule, and everything in the universe emerges from that simple rule? So in order to make that even a conceivable possibility, we have to imagine going underneath notions like space and time and so on. We just can't pack all the information that we have about the universe into some simple rule if we expect that that rule is going to sort of show evidence of the things that we already know about the universe. Well, so the thing that I first kind of wondered about in the 1990s and got quite a long distance with, actually, and that finally sort of came together about a year and a half ago, was the realization that, yes, there is actually a way to understand how the universe can be constructed, and let me start talking about how it works. So the basic idea, let me kind of give you the big view first. This is kind of a visual summary of what's going to happen here. And I'm going to go through a bunch of pieces of this, and there is tremendous depth of sort of detail of this, which I'm not going to go through. But some parts of this are kind of necessary to understand what I'm talking about with consciousness and so on. So the basic idea is we're going to start from the simple rule. It's going to grow a structure that represents space. It's going to show things that correspond to quantum mechanics and so on. And we're going to kind of walk around this picture. So the idea, it's a little bit like in, so the first thing to think about is what is space? Normally in physics and so on, and kind of in mathematics, one just thinks of space as sort of a background. And all one says is one can put things at different positions in space. There's no notion of space is a thing. It's just sort of the background in which other things exist. So back in the past, people wondered whether something like water worked that way as well. But we know that, in fact, when we have something like water, it's made of discrete molecules. There are a bunch of discrete molecules bouncing around, although on a large scale, water seems like a continuous fluid. So one of the things that's sort of fundamental to our theory of physics is that's kind of how it works in physics as well, that there are kind of atoms of space. There are sort of elementary points that exist, and space is made from a network of those elementary points. So you can think about it in a very abstract way. It's basically all there is are elements, and the only feature of elements is that they have identity, and you know which element is the same as which other elements. And these elements have relations between them, and these elements and relations can be thought of as describing a graph or more completely a hypergraph. And so, for example, this might be a very simple collection of elements, sort of atoms of space, and all you know is which atom of space is connected to which other atom of space. You don't know, there's no notion of position. There's no way that we're saying this is placed at this point in space. There is no space. It's just something which is described by this kind of structure. So what you can then think about is let's imagine a rule that says, for example, that every time we see a piece of one of these structures that looks like this, we're going to transform it into this. So let's try running that rule. Here's what we get. In successive steps, we build up this more and more complicated network. Here's a version of that network. We can keep going. We make all kinds of complicated networks. Sometimes we make networks, here's an example, where we make a network which corresponds to something we can recognize. It just corresponds to a two-dimensional grid. Sometimes we might have a network that corresponds to, here's one that corresponds to something that seems like a curved two-dimensional grid. But remember, what we're seeing in these pictures is these are just renderings of this network. All that the system intrinsically has in it is a bunch of points, a bunch of discrete atoms of space, and information about how different atoms of space are connected to each other. Everything else is just kind of in the way that we are presenting it. So the concept of our theory of physics is basically all of the universe is just a giant hypergraph that consists of a very large number of atoms of space. Perhaps in the universe, maybe around 10 to the 400 atoms of space. And all that we know about things is the connectivity of those atoms of space. And the surprising fact is that something that behaves to us like ordinary continuous space emerges as a result of just this very big collection of these atoms of space. It emerges in a way that is, in many mathematical senses, very similar to the way that the continuity of fluids arises from sort of the discrete effects of these individual molecules underneath. In some sense, you can start seeing how there's a correspondence between some of these ideas, but it's very important in something like a fluid like water that these molecules are sort of bouncing around randomly. That bouncing around randomly is captured by the second law of thermodynamics, something that's been very hard to understand in kind of the traditional development of mathematical physics. It turns out the second law of thermodynamics is one of the consequences of computational irreducibility. But it's that the sort of the computational irreducibility produces the randomness of the molecules, which when we look at it on a large scale, reads to us like the continuity of a fluid, or in the case of space, the continuity of space. So one feature of our models is that space and time are very different kinds of things in these models. Space is this extent of this hypergraph. We can say, well, actually, we can start talking about things like what's the dimension of space. This space doesn't intrinsically have any particular dimension. And by the way, when we draw the space, just to emphasize it again, all that we know for sure is what's connected to what. So all of these pictures, even though they look very different, represent the same version of space. We can do things like ask, what's the dimension of the space? You know, this kind of looks two-dimensional. We can kind of measure the dimension by saying if we start at a point and we just look at how many points do we get to if we go a distance r on the graph away from that point, we find that if the thing is going to approximate two-dimensional space, it'll be r squared. If it's going to approximate three-dimensional space, it's r cubed. In general, it will be some fractional dimension. And but we can identify a definite effective dimension for space as a limit as we have a sufficiently large hypergraph. And there are all kinds of interesting cosmology things about dimension fluctuations in the universe and the way that the early universe works in changing dimension and so on. But that's we will get off topic if we start talking about that. So in any case, the basic idea here is that everything in the universe is just made of space. Space is all there is. And so everything that is, for example, particles like electrons and photons and things, they all just have to be features of space. And the way we can think about that is, it's kind of like what happens in a fluid like water. We can have something like a vortex, which is some sort of stable piece of the fluid, that's some sort of stable structure in the fluid that can move across the fluid. And the way we should think about particles and things like that in this notion of space is as something like that kind of topologically stable thing, like a vortex, going through this thing that is just this hypergraph that represents space. And by the way, in case one gets too kind of proud of our presence in the universe, one of the things that one realizes happens is the vast majority of activity in this hypergraph has the sole consequence of knitting together the structure of space. And everything that we are sort of interested in, all the particles and photons and electrons and all that kind of thing, represents perhaps 1 part in 10 to the 120 of the activity that's going on in the hypergraph that represents the universe. But I was just going to say that one of the features of our models is that space and time are very different in our models. Space is the extent of this hypergraph. Time is kind of the inexorable computational rewriting of the hypergraph. So time, the progress of time, is the performance of computation. And so you might say, well, gosh, haven't you learned that, you know, space and time are the same kind of thing? That's been something people have believed in physics for 120 years or so. Well, it turns out that I think that was a mistake, actually. It was a Hermann Minkowski mistake as a result of going after some elegant mathematics to have the idea that conceptually space and time are the same kind of thing. I think they're not conceptually the same kind of thing. The question then is, if space and time are not the same kind of thing, how do we get all the features of space-time and relativity and so on? It turns out to be rather easy. The key observation, and this is going to be important in other things I'll talk about, is, and this is where things start to get a little bit conceptually complicated. Imagine that you are an observer in this universe. One feature of the observer in this universe is they have to be part of the universe. The observer is made of nodes of hypergraph, just like the rest of the universe is made of nodes of hypergraph. So then the question you have to start asking is, how does an observer embedded within this universe, what can they even observe about this universe? So let's take a very extreme example of an observer embedded in a universe like this. Let's say the observer is like a Turing machine, which just has one little head where things happen in the system. So if there was a Turing machine updating this hypergraph, it might have a head that goes to one node and then it jumps to another node, updates that, jumps to another node, updates that, and so on. Well, imagine that we are observers in that universe and we're part of that whole story. And we say, has something happened somewhere else in the universe? Well, we don't know whether anything's happened anywhere else in the universe until we've been updated. And in the end, what you realize is the only thing we can ever be sensitive to is the kind of causal relationship between updating events. So all we really care about, all we can ever measure, all we can ever sense is how we are causally connected to other things in the universe. What is the causal graph that represents the causal relationships between updating events in in the history of the universe? Well, to give you some sense of how that works, let me see. You can, let's see, I've got lots of pictures of this. Well, let me show you. This. So this is a very simple system, simpler than our whole hypergraph thing. Just a system where there are a sequence of A's and B's, and there's a rule that says whenever you see BA, replace it by AB. Okay, so that rule has the feature that you can, and these yellow pieces show where that rule was applied. So there's some freedom in where you apply this rule. You don't have to apply the rule. You're not being told where to apply the rule. It's just whenever you see a BA, you might replace it by an AB or you might not. So one important feature of this particular rule is it has a property that we call causal invariance. For people who know mathematical logic, related to the Church-Rosser property and confluence and so on. It's it has the property that it doesn't matter in what order you do. Well, actually, this particular rule has the property that regardless of what order you do all these updates in the end, it will always sort the string into A's first and then followed by B's. But the important thing for our purposes is we can look at these these events that are updates in these strings, and we can ask, what are the causal relationships between these events? And so we can draw a causal graph that shows for this update to happen, this update has to have happened because it's going to use one of the outputs from this update is going to be used as an input to this update, and so on. And so we can set up this causal graph that represents the causal relationships between those updating events. And the big fact is, when there is this causal invariance property, the causal graph is not dependent on the structure of this causal graph does not depend on the detailed updating order of these underlying events. So talking about that in terms of the universe, we've got this rule that says when you see a piece of hypergraph that looks like this, updated in this way. But the crucial point is, we don't say, when we set up that rule, we don't say where those rules should be applied. We just say, do those rules wherever you feel like doing them. And the key point is that the causal graph that we get out from doing that is not dependent on which order we chose to do those rules in. So maybe I won't go into this in tremendous detail, but one of the things that then emerges is when you start looking at just causal graphs, you very quickly realize that you are forced to satisfy special relativity, and you can, so essentially what's happening is your notion, all you know about is this causal graph that's telling you the causal relationships between events. But if you want to have an idea of what's going on in the universe, and this will come up later, you kind of have to construct for yourself a notion of what counts as space and what counts as time. All you really know about is the causal relationship between events. But you construct for yourself a notion of there are these things which are happening simultaneously in time at different places in space. In the terminology of relativity, you're constructing a reference frame with which to view the universe. You're constructing something where you say, these events we consider to be happening simultaneously, they happen at the same time at different places in space. And the point is that the fact that this fact about causal invariance and the independence of the causal graph, that it turns out to be the thing that allows you to make the same conclusions independent of what reference frame you pick, which is the basic statement of special relativity. So even though we started from a system in which space and time behave very differently, we end up with a system in which they follow the same rules as standard relativity. Actually, we can go further than that, and it turns out that in our systems, in much the same way as the equations of fluid dynamics arise from the dynamics of individual molecules, the continuum limit, the sort of effective large-scale behavior of all of those hypergraphs and so on, subject to various conditions, is exactly Einstein's equations for the structure of space-time. So we can measure, just as we talked about measuring dimension, we can measure curvature, effective curvature of these hypergraphs, and we can look at kind of the dynamics of that curvature, and it turns out that we get exactly the equations that you expect from for the equations of space-time. One feature that I might mention about that is sort of a key fact about space-time is straight lines, GD6, shortest paths. If in a flat space, a shortest path is just a straight line. In a curved space, a shortest path will be deflected by the curvature in the space. That's what in general relativity is the source of gravity. Well, in our models, we also have GD6 and the GD6 on these graphs, and the GD6 can be reflected. And it turns out that the rule for the deflection of GD6 is proportional to essentially the amount of activity that's going on in the graph. And so what turns out to happen is that energy turns out to be essentially the amount of activity that's happening in the graph. Slightly more formally, it's the flux of causal edges through space-like hypersurfaces. But the sense is what deflects a kind of the trajectory of a thing in this space is the presence of activity in the graph, which is identified as energy in our kind of interpretation in physics. Okay, so that's a little bit on sort of how space and time work. We're going to get to consciousness, and we're going to see in a bit how all these things and the emergence of even Einstein's equations depends on a certain feature of the way that observers work. Okay, so the other big thing in physics is quantum mechanics. And one of the things that's really remarkable in our models is that quantum mechanics is something that is absolutely inevitable and unavoidable in our models. So I mentioned we've got this underlying rule, it's updating this hypergraph, and it's set up so that it just says, here's the rule, use it wherever you want. Well, so the question is, well, what about different possible updating orders? What about different places I can do this updating? Doesn't each of those different updatings lead to a different history for the universe? Well, the thing I was just explaining is that when it comes to an observer measuring causal relationships, no, it always leads to the same set of causal relationships. But we can also ask, in general, does it lead to a whole bundle of different possible histories for the universe? And the answer is that it does. And so let's remember the sort of big distinction between classical mechanics, classical physics, and quantum physics. In classical physics, definite things happen. You know, you throw a ball, it goes in a definite trajectory. In quantum physics, the big idea is it isn't the definite things happen, sort of all possible trajectories are followed, and we merely get to measure certain things, certain probabilities about what the outcome is. So in these models, what happens is we can imagine just tracing all possible histories for the universe. We call it a multi-way graph. And this multi-way graph here is tracing all the possible histories, all the possible updates that could happen in this universe. So we could take maybe a simpler example of that, if I can find my little mouse. There we go. Let's see. Well, here's a simpler example. This is just just rewriting strings rather than hypergraphs. This is just showing sort of the multi-way graph of all possible rewritings. So every node here, every little rectangle here is like a complete state of the universe. And this is now showing us, in a sense, what quantum mechanics is saying is there are all these different possible states of the universe that are produced. Okay, but now we can ask all sorts of things about that, and we can ask, for example, we can say, how would an observer measure what's going on here? Well, maybe I should say one other thing first. One question is, in this multi-way graph, we can say, so as we go down the page, we're kind of going through successive steps in time, just like in the case of relativity, we can essentially pick our notion of time differently, depending on different observers could pick their notion of time differently. So for instance, let's see, we could do something like this. We could say, these are our time slices. We could do something like this. We could say, these are the time slices. These are the reference frames that we're using to kind of measure what's happening in the universe. We could make something more exotic like this. It turns out that these different reference frames, we call them quantum observation frames, these are essentially what correspond to different possible quantum measurements that can be done. And essentially what's happening is that at each step here, we can think of these are possible quantum states of the system. In some cases like this, we might say we're sort of freezing things to believe that this is the final state of the universe, and time is frozen after that final state is reached, and we see progressive sort of decoherence with the rest of the universe. But we can so this is kind of the structure. Now one thing we can ask is, if we say, well, if we take one of these slices, what is the relationship between these different states of the universe at each slice? And we can define what we call a branchial graph. A branchial graph represents the relationship between the different possible branches of history for the universe. And this is showing kind of the ancestral relationship between those branches. It's showing it's kind of giving us a map. In the quantum mechanical sense, this is a map of the entanglements of quantum states. This is a map of quantum entanglements. And so this branchial graph is the analog of what is space in space-time is the branchial graph, the map of entanglements in this multi-ray graph. So, okay, again, slightly bigger picture. So what happens is, in our model of physics, we've got this kind of spatial hypergraph. We've also got, when we look at this multi-ray graph that represents all these different quantum histories, we've got another kind of graph, this branchial graph, that represents the relationships between those quantum histories. So one big fact that I was really excited about when we discovered it about a year or so ago is that what is the Einstein equations that describe essentially motion in physical space, describe things like gravity here, the analog of the Einstein equations in branchial space turns out to be the Feynman path integral for quantum mechanics. So in other words, what is a story about geodesics in physical space in space-time is a story about the evolution of quantum amplitudes in branchial space. So in a sense, general relativity and quantum mechanics are the same theory, simply played out in different kinds of space. And when you deal with things like black holes, there's sort of an interface between physical space and branchial space, and all kinds of interesting things happen. Okay, so that's kind of the rough picture of sort of our model for physics. Okay, so what does consciousness have to do with any of this? Let me first zoom out again and talk about what I used to think was the sequence that would lead to consciousness, which is kind of life, intelligence, consciousness. You know, I've talked about kind of these things about the computational universe for decades, and people would regularly ask me sort of, so what does this mean about consciousness? And I would say, I don't really have anything to say about that, I don't know. But let's talk about the more junior versions of things like life and intelligence and so on. So one question is, what's an abstract definition of life? Life on Earth, pretty easy to define. It all comes from a common ancestor. It's all got RNA, it's all got proteins, it's all got all these kinds of things. When we say, you know, we've got the spacecraft going to planet X, and we've got to say, when you scoop that soil up, is there something alive in it? Yeah, we might find RNA, but more likely we want some more abstract definition of life. So I think the net of many attempts at that is, in the end, the only thing we can say for sure is that life involves sophisticated computation, which you might have thought was a non-trivial constraint until you realized from the principle of computational equivalence that actually sophisticated computation is completely ubiquitous in computational systems, in formal systems. So then you go on to intelligence and you say, well, is that something really special? You know, we know the human example, you know, what happens to the extraterrestrial intelligences? How do we tell whether the signal from wherever is a sign of extraterrestrial intelligence and so on? It's kind of a philosophically doomed issue, I think. But the one thing that I think we can say for sure is the thing that we might think of as intelligence is, again, this story of it's doing sophisticated computation. Without that, it probably doesn't make the cut. But it's not clear you can make any other kind of bright line distinction. So now the question is, well, what about consciousness? So what I realized is that actually I think consciousness is a step down from these stories about life and intelligence. I think that consciousness, in the way that I'm interpreting it at least, is a restriction on what systems can do and what observers can do. So the thing that I realized is that in setting up physics, we are talking about observers who observe space-time, who observe the quantum universe. And the question is, what can those observers do? And the critical thing turns out to be those observers, in a sense, force themselves to have a certain thread of experience. this comes incredibly naturally to us humans. That's just the way we think about things. That's the way we set our physics up and so on. But what we're essentially doing is we think about the universe, we think about space and so on. In space, there are all these atoms of space. They're all getting updated. Lots and lots of things are happening. It's all over the place. But what is the coherence of that? Can we tell a coherent story about what happened? Can we define something that we would think of as being sort of a thread of experience in that picture? Well, it turns out that the way we set up physics with these things like reference frames and all that kind of thing, that is a story of insisting that we are telling this kind of sequentialized thread of experience type story. And so what we realize is that this kind of, so here's kind of a way to think about it. Imagine you're an observer in this computationally irreducible universe. What features do you know you have? So one feature you probably have is you are probably computationally bounded. You as an observer are not capable of untangling all that computational irreducibility. You are somehow computationally bounded. And that one statement that the observer is computationally bounded turns out to give one a huge amount of mileage. So let me give you an example of a sort of a minimal case of that. Let's talk about thermodynamics. So when you have, I keep on talking about, a bunch of molecules bouncing around a box or something, people just realized, back in the late 1800s, they invented the Second Law of Thermodynamics. They said you start off all these molecules in an ordered configuration, and pretty soon they've jiggled themselves around and they're all completely disordered, and it looks like the entropy of the system has increased. Okay, when you try and tighten up that statement, it has always fallen apart. Because if you say, how do you measure the entropy? How do you measure the number of possible states consistent with what you're measuring? Well, it depends on how well you can measure what's going on. If you could look at the position of every single molecule, you would be able to, you wouldn't say the thing looked random. You would just say, well, it just comes because I solved the equations and here's how the molecules ended up. The reason that you say, oh, it looks kind of random is because you are a computationally bounded observer of that gas. In the lingo of statistical mechanics, that's the coarse graining assumption of statistical mechanics. But it's always been quite obscure what counts as a valid coarse graining in statistical mechanics. What is the thing you're not allowed to do? What's the microscope you're not allowed to have on this, looking at this gas? And so the thing we realize is, once you say that you as an observer are computationally bounded, you can only do a limited amount of computation, you are fighting against computational irreducibility. This gas is showing computationally irreducible behavior. You can only make a computationally bounded observation. That right there gives you the second law of thermodynamics. I mean, there's more detail to it, but that's the basic idea. As a computationally bounded observer, you inevitably observe that the gas behaves according to the second law of thermodynamics. Well, it's the same thing in relativity. The fact that we identify a definite notion of space and time is also a consequence of the fact that we are computationally bounded observers of the spatial hypergraph and its evolution. If we weren't computationally bounded observers, we could foliate time in some incredibly elaborate way that would make it look like we didn't obey special relativity or general relativity. But it's because we are computationally bounded in the way we can set up those reference frames and so on that makes us necessarily follow special and general relativity. Okay, what about quantum mechanics? Well, in quantum mechanics, we end up with the same kind of story, but it's a little bit more of a brain twister, because what's happening in quantum mechanics is we've got an observer. We've got this branching and actually also merging, this branching and merging multi-way graph that represents the thread of histories of all the different histories of possible histories of the universe. But as observers inside that multi-way graph, we have the strange situation that we are branching brains observing a branching universe. And the question is, how does a branching brain observe a branching universe? And the answer is, if the brain is going to make sense of the universe, the brain has to just sort of say, well, I'm going to assume these two things are equivalent. Okay, in the language of mathematical logic and so on, the brain is effectively making what are called completions, which are essentially, these multi-way graphs are equivalent to theorem-proving systems, and you can think of these things as essentially lemmas that the brain is making, assuming that certain things in the universe are equivalent. So the big point is that a branching brain can, in the same way that we pick a reference frame to refer to points in space, we're picking this kind of way of knitting together these different branches of history. And the big point is that, and this is a sort of a formal fact, is that it's possible to do that consistently. It could be the case that we would come up with all of this knitting, we would come up with all these reference frames in relativity and quantum mechanics, we would make a beautiful reference frame, but as the universe evolves, it would kind of show us that we didn't know what we were doing. It would just fall apart. That reference frame would no longer be a good way to refer to the universe. But it's a consequence of the whole structure of these models and computational irreducibility and causal invariance and so on, that it is possible that when you have constructed the right kind of reference frame, the right kind of sort of completion structure, it will always be preserved. It will always be consistent. You can consistently do it. So in other words, it is possible to have a consistent view of the universe in terms of space and time, in terms of definite histories in quantum mechanics. And it is possible for an observer to construct such a thing, and it will not fall apart as a result of the actual behavior of the universe. So and again, the kind of the notion is that this is something where, well, yes. So you can think of this thing with quantum mechanics as essentially defining reference frames in quantum mechanics, and that's so the point here is that in the interpretation, okay, so what then sort of is consciousness and how does it relate to what we're talking about? My basic assumption is that sort of consciousness is all about, at least the part of it that's important for me, is all about, we can talk about other parts because I've thought about those too, but is the part that is kind of producing this sort of sequentialized thread of experience. And the claim is that it is that sequentialized thread of experience that we as observers of the universe think exists that causes us to attribute to the universe the laws of physics that we attribute to the universe. And the non-trivial formal fact is that it's consistent to do that. Okay, so now the question is, what if we were very different from the way we are? Is there an alternative way of kind of perceiving the universe? Is there, and for example, the fact that we are roughly the size we are intermediate in scale between the place where the effects of relativity are important and the place where the effects of quantum mechanics are important. And that's probably why we end up with the descriptions that we do of the universe. If we were really huge, if we were the size of planets, even if our consciousness, if our existence, existed on two sides of an event horizon, a cosmological event horizon or something, we would necessarily have a very different perception of the way the universe works. We would not be able to construct the same kind of notions of space and time that we construct. And so I think that's, and if you start thinking about, so for example, the fact that we construct notions of space and time like we do is kind of a consequence of the fact that the speed of light is pretty fast compared to the speed our brains work at. The things we look at, we look around, we see a few tens of meters away. It takes light nanoseconds to reach us from tens of meters away, but it takes our brain milliseconds to process that. So as far as our brain is concerned, at every moment in time, we have a sort of single gulp of this is the structure of space at every moment in time. If we were at a different scale, we would have different conclusion. We would not see space and time in that way. Even if we were, if our main perception mechanism was olfactory, for example, and we had to wait for the scent to reach us in the wind, we would also not have the same perception of space and time because we wouldn't have this idea that space exists at moments in time. Well, just to kind of, so then the question is, can we imagine sort of different views of the universe? Well, let me give you kind of a bigger story about these models of physics, and I do want to wrap up soon because I really want to. But let me just let me ask this question. So you might say, okay, you've got this model of physics. Eventually, you discover there is this rule. It represents all of the universe. It represents all of physics. It reproduces everything about the universe. And I present you with this rule, and you say, "Gosh, that's really weird. Why is it that rule and not another rule? Why did our universe get that particular rule? If it's a simple rule, how come we broke the whole sort of Copernicus idea and we got a simple rule, whereas those other guys over there in another universe got this very complicated rule? How can that be? Why are we that special?" Okay, so here's how I think it works. And it's something perhaps kind of bizarre at first. So I've said that with this particular rule, we imagine that the way that the universe gets updated is you apply this rule wherever you feel like, so to speak. There's a whole multi-way graph of possible histories from possible different ways to apply the rule. Okay, so you can go even further than that. You can invent a rulal multi-way graph in which not only do you pick all the different possible places to apply the rule, you also apply all possible rules. And you say, so you make this multi-way graph, but instead of these branches corresponding to different places to apply a particular rule, they're different rules. And in fact, in the world of computation theory, that's like having it's kind of like having a maximally non-deterministic system. You know, you can have I wrote something about rulal space and Turing machines. You can think of it as kind of the ultimately non-deterministic version of Turing machines. All possible things could happen. So, okay, so in this rulal space, we get this giant rulal multi-way graph of all possible histories, of all possible sequences of rules in the universe. Okay, so then how do we then we embed ourselves in that rulal multi-way graph. And then what do we observe? Well, just like all these other things, we end up building rulal reference frames that are essentially description languages for describing what happens in the universe. And any particular rulal reference frame will attribute a particular rule to the evolution of the universe. But the key fact is that because of causal invariance, which is inevitable in this rulal multi-way graph, because of causal invariance, in the end, all of those different views of the universe are equivalent. So in other words, we can pick this description language, we can pick that description language, it doesn't matter in the end. They're all equivalent. But in terms of the laws of physics that we imagine are there, those laws of physics will be bizarrely and incoherently different. So in other words, we have a particular description language for the laws of physics that comes about because of the particular rulal reference frame that we've picked, but there can be utterly incoherent ones. So, you know, the aliens, even though they live in the same universe in a sense, don't have to have even vaguely the same sense of what's going on in the universe. They simply are they can pick a different rulal reference frame, at which point they have an utterly different description of what's happening in the universe. So you can ask questions like, you know, how would consciousness survive that? Well, you can imagine this kind of sequentialization happening in different rulal reference frames. You can imagine a completely different sequentialized view of the universe. You can also imagine views of the universe that are not sequentialized. You can imagine, and basically what's happening is, okay, the final big picture here is, in a sense, you can think of sort of a lot of science as being this struggle between computational irreducibility and computational reducibility. Computational irreducibility is what kind of makes things interesting. Computational reducibility is what makes things predictable, what makes science possible. And so, in a sense, our existence and certainly our consciousness seems to depend on finding a certain pocket of computational reducibility within this whole computationally irreducible universe of possibilities. And so the sort of key fact about computational irreducibility is that within any computationally irreducible system, there will always be actually an infinite number of possible slices of computational reducibility that exist. Each one of those slices of computational reducibility are essentially a collection of laws of physics. They're a description of the universe, but they can be utterly different from our description of the universe. So that's more or less there are various tentacles to this whole thing, but that's more or less the story of kind of sort of thinking about things starting from sort of this fundamental theory of physics, trying to understand sort of one import of this computational theory, this fundamental theory of physics is the universe is computational all the way down. And once you know that, you can then kind of build back up and say, what are the implications of that fact for all the other kinds of things we might want to think about? And I would say that I'm embarrassed at how little I know about the history of philosophy. People have been sending me mail last week or two telling me, Immanuel Kant said things that are very like what you're saying, and that's very interesting. And I'm impressed that he could figure these things out because there was lots of science that wasn't known then. And I'm sure there are lots of other things that people have said that are closely related. And I'm curious because I think anytime one understands those connections, one is pulling in other potential implications of this. And I would say that as a very practical person, I spend my life building computational language that sort of is the interpolation between the computational universe and all of the complexity and what can happen there and our efforts at human thinking. I mean, I spent most of my life building this thing called Wolfram language, which is a computational language to try and describe the world in computational terms in a way that's useful to us humans, but that can make use of what is possible in the computational universe. And so for me, these kinds of questions about sort of the nature of consciousness has a very practical implication, because one of the things that we've never figured out how to do is have a good way to get us humans to really understand computations that don't happen sequentially. And I think with this kind of my sort of emerging, at least personal understanding of consciousness, it kind of now makes sense that that's been so hard, because it's a really fundamental feature of our kind of existence, it seems, and the way that we construct our laws of physics and so on, that that we have this kind of sequentialization. And by understanding more about how this works in physics, we're getting a bunch of ideas about how maybe we can get a little distance towards having us, with our sort of human capabilities, understand how to sort of program in different reference frames and so on to think about doing distributed computation. Okay, let me stop there.